Okay. So I believe like whatever I have told you till now, everything is clear. Should we revise or should we move forward directly?
So can we have a short
He has
revision?
attended the session or have was the recording, right?
So
Yes.
can we have a short
Yes.
revision, sir?
Sorry.
Can we have a short revision?
Short revision. Okay. So yes, we started matrices, and in this, we know already like how do we represent the elements in it, right? With the help of using rows and columns, right? Uh, Suppose I have to show like what is the address of this particular element. So yes, it will be nothing but A11, first row and first column. This is nothing but second row but third column, A23, right? So this was the representation method, construction of any matrix. So sometimes there some formula will be given to you in form of I and J, and you have to form each and every element of the matrices with the help of the formula. You just have to put the value of I and J, right? Then we did types of matrices, row matrix in which we will be having only one row, column matrix in which we will be having only one column. Rows can be any number. Yes. Square matrix in which rows and columns will be equal. Diagonal matrix in which diagonal elements will be non-zero elements, other elements will be zero. Scalar matrix in which all the diagonal matrix will be same. Then identity matrix in which every diagonal element will be 1 and other elements will be 0. Null matrix in which every element will be 0. Upper triangular matrix in which lower part will be 0 and upper part will have significant numbers. Vice versa with lower triangular matrix, right? Then we did operations on matrices. So if we want to add any two matrices, what we'll do, we'll add element to element. Yes, corresponding elements will add to add the to add any two matrices. Uh, to add any two matrices, the order should be same, right? Similarly, for equality of matrices, if we want to compare two matrices, the order should be same, and we can compare element to element. Yes. Then we did summation. So summation we can do element to element, right? Order should be same. Then we did some properties of the matrices in which we understood like it is commutative, associative, and if we add any null matrix to any matrix, it will not change, right? Minus A will be additive inverse of A. Cancellation law works for these matrices. Then we did subtraction. For subtraction also the same rule will be applicable. Scalar matrix, scalar multiplication. So suppose if I want to multiply with any scalar number with any matrices, so each and every element of inside the matrices will be multiplied with that scalar quantity. Yes. Then we did some properties, some basic properties of this scalar multiplication. Then we did matrix multiplication. How do we multiply any two matrix? So I told you, like we will first we have to multiply. We have to see what is the order. Suppose we have 3 cross 2 and 3 cross 4, will not be able to multiply. Every time the number of columns in the first matrix and number of rows in the second matrix, that should be equal. Then only you will be able to multiply. Yes, if we are going to multiply 3 cross 4 with 4 cross 5, so we'll be getting a matrices with 3 cross 5. Okay. Now, I told you how to multiply. Suppose you are taking one row of it. So you'll multiply this one row with one column of the other matrix, and you'll multiply corresponding elements, 1 with 3, then 2 with 1, and then 3 with 0. And you'll add all these three products, and that will give you one single element. Then you'll multiply this first row with second column, then third column, and that's how you'll be getting different elements. Yes, if you have chosen first row and then you are multiplying with columns, so the elements whichever you are getting, that will be written in the row order. Okay, then we did some properties of this matrix multiplication, that AB is not equals to BA, that is most important property. Associative property holds for it, distributive property holds for it. Yes. Then we did transpose of a matrix. Transpose is nothing but when we convert each and every row in the column as a column, and columns get converted as a row, right? Then we did some properties of the transpose. That transpose of a transpose will be nothing but the original matrix. Yes. A plus B dash, that will be A dash plus B dash. Yes. So similar to that, we discussed many properties of this transpose thing. Then trace of a matrix. Trace of a matrix is nothing but when we add all the elements of the diagonals, that gives you the trace of a matrix. Yes. Now also we did some basic properties of the trace of a matrix. Then we were doing positive integral powers of a square matrix. Suppose we want to calculate what is a square, so we have to multiply a with a. Suppose we want to calculate a cube, so I have to multiply a square with a, and I'll be getting a square by multiplying a and a. Yes, so that was positive integral powers of a square matrix. And in the end, we did matrix polynomial. So matrix polynomial is nothing but suppose you have been given a polynomial equation, and in this polynomial, it is saying that matrix A satisfies this particular polynomial equation. So obviously in place of X, you can place the matrix A, and that will be equals to 0. Yes, similar to that 0 or root thing. Yes. And wherever you have the constant value, you'll multiply the identity matrix with it, and you'll write this thing in the matrix format. Yes. So till here we have done in the last class. Let's proceed further. Okay. Now, spatial matrices. Spatial matrices is nothing but let's talk about two matrices, symmetric and skew symmetric matrices. Anyone who's having any idea about symmetric and skew symmetric matrices? Okay.
Symmetric matrices are
Yes.
those with diagonal elements as the mirror.
Yes.
So
The diagonal elements will be working as a mirror, and if you'll transpose it, you will be getting the same value. Yes. If I transpose this square matrix, you will be getting 1, 2, 3. This row will be converted into the column section, right? 1, 2, 3. This 2, 4, 5 will be also converted to the column part. This 3, 5, 2, this also be converted to the column part. So you can see that this is still 1, 2, 3, 2, 4, 5, 3, 5, 2. Yes. So that is called symmetric matrix. Yes, in symmetric matrix, always the transpose of the matrix will be similar to the original matrix. Yes, then there is another thing, that is skew symmetric matrices. Skew symmetric matrix is nothing but in which when we will do the transpose, it will give you nothing but a negative value of the original matrix. Means what? Suppose you have 1, 2, 3, and you have 2, 4, 5, and you have 3, 5, 2. And let's say this is -2, -3, and -5. So if I do the transpose of this matrix, I'll be getting what? This 1, 2, 3 will be converted to the column thing, right? -2, 4, 5 will come here. Yes. And this -3, -5, and 2. -3, -5, -2. Sorry. -3, -5, 2. Only 2. Yes. So if I transpose this, you can see that this is 1, 2, 3. This is 1, -2, -3. If this is -2, 4, 5, this is 2, 4, -5. This was -3, -5, 2. This is 3, 5, 2, right? So suppose if I multiply this whole matrix, this original matrix with negative sign, what will happen? So this will give you what? -1. That is not matching. -2, -3, that is matching. Now, this -2 will become 2. This 4 should be what? -4. This is not matching. But this is what? -5. This is matching. Now, minus of -3, that is 3. Minus of -5, that is 5. and minus of 2. Yes, so this is not matching. So these three elements are not matching and we want it to match after the transpose thing. Yes, so this should be nothing but 0 itself. Forget about this thing. You can remember it like this. After the transpose, there should only be the difference of the negative sign. Yes, so every skew symmetric matrix will be having 0 in the diagonal. Yes, and you will see that the difference between the original matrix and the transpose matrix is only of negative sign. Any doubts in this? Anyone? Should we continue?
Yes.
Okay. Now let's move further. So in skew symmetric matrix, there will be always 0, 0, 0 in the diagonal elements, right? That I told you. Now, point number 2, which is important to us, every square matrix, we can write every square matrix in the form of symmetric matrix and skew symmetric matrix. So suppose you have any normal matrix. So if you will do half of A plus A dash is what? Transpose of the matrix, right? So when you will add A and A dash and divide it by 2, so A plus A dash by 2, this will show you the symmetric matrix, and A minus A dash by 2, that will give you skew symmetric matrix. Yes, so any normal matrix can be written in the form of symmetric and skew symmetric matrix. Are you getting this point? Suppose you have
This B and C.
okay, let me tell you. Suppose you have a matrix. Let's take a matrix. 1, 2, 3, 4, 5, 6, and this is 7, 8, 9. Let's take this. And if I do A dash, what will be A dash? This 1, 2, 3 will come here, right? 1, 2, 3. This is 4, 5, 6, 7, 8, 9. Okay. So now what I'm doing, let's say A plus A dash by 2 we are doing, right? A plus A dash by 2. So if I do A plus A dash by 2, what will happen? We'll add the elements and divide by 2, right? So 1 plus 1 by 2, that is nothing but 1. 2 plus 4, 6 by 2, that is nothing but 3. 3 plus 7, 10 by 2, that is 5, right? Now, 4 plus 2, 6 by 3, that is 3. 5 plus 5, 10 by 5, that is 5. 6 plus 8, 14 by 2, that is 7. 7 plus 3, 10 by 2, that is 5. This will be 7, and that will be what? 9 itself, right? So you can see, is this a symmetric matrix? 1, 3, 5, 3, 5, 7, 5, 7, 9. This is the diagonal element 1, 5, 9. And about this, the lower part and the upper part, these two are similar, right? This is 3, 5, 7. This is 3, 5, 7. If you'll do the transpose of it, you will be getting the same values. Yes or no?
Yes.
Yes. So this is a symmetric matrix, right? And because it's a symmetric matrix, I have given a name to it. Let's say B. Okay. Again, let's create a matrix C in which what we will do? This C is nothing but A minus A dash by 2. Here we were doing A plus A dash by 2. Here it is A minus A dash by 2. So A minus A dash by 2 will be what? 1 minus 1, 0, 0 by 2 will be 0. Then 2 minus 4 by 2, that is minus 2. 3 minus 7 by 2, that is what? Minus 4 by 2, that is minus 2. And that should be minus 1, right? I have to do by 2 also. 4 minus 2 by 2, that is 1. Then it's 0, and then it's minus 1. Then it's what? 2. Then it's 1, and it's 0, right? So if I see 0, minus 1, minus 2, minus 1, and here we have 1, 2, 1, and 0, 0, 0. Is it a skew symmetric matrix? If we'll do the transpose, what will happen? this will be getting 0, -1, -2, which we have in row 1. That will come in column 1, right? 0, -1, -2. And there will be a difference of negative sign only. Yes. So now I can see that there is a matrix B, there is a matrix C. This B is nothing but symmetric matrix. This C is nothing but skew symmetric matrix. And if I add B and C both, I'll be getting nothing but A only. Yes, 1 plus 0, that is 1. 3 minus 1, that is 2. 5 minus 2, that is 3. Yes. So what I have done, I have written the same matrix in the form of summation of matrix, symmetric matrix and skew symmetric matrix. Any doubt here? Any doubts?
So,
No,
sir,
sir.
what would we say the identity is?
Sorry?
Can you go back to your
Yes.
like what file? Yeah, what did you say? Square matrix can be uniquely expressed as a sum of a symmetric matrix and a skew symmetric matrix.
Sir, I have a question.
Yes.
Yeah.
Sir, what we call these B and C, like the B is a symmetric matrix of A. Like,
See, what we
can we
have
need
done
to say
actually.
something now for B or C?
See, what we have done
And how
actually.
we use this in a question?
Let me tell you. We have done nothing but like you have a simple matrix. Now you have done nothing. You have just break it into two different matrices. If you will add these two matrices, you'll be getting the same original matrix. Okay. And you have divided this matrix in such a way that this particular matrix is a symmetric matrix and this particular matrix is a skew symmetric matrix. In simple words. Are you getting this?
Okay, got it.
Yes. So we have done nothing but we have done the partition of a simple matrix into two different matrices. One is symmetric matrix, another is skew symmetric matrix. And what is the methodology to do it? So to get the symmetric matrix, you have to do half A plus A dash. To get the skew symmetric matrix, you have to do half A minus A dash. Simple. Yes. Now, let's further talk about if A and B are symmetric matrices, it's a property, right? If A and B are symmetric matrices, then AB will also be symmetric. Yes, if AB is equals to BA. What does it say? If A and B are symmetric matrices, then AB is symmetric. AB will also be symmetric if AB is equals to BA. Simple. This is a property which you can remember as it is. Any doubts in this? These are simple properties which will help you in some particular questions. Although we need not to go into that much deep. You just have to remember the what say chronology or say the terms actually. What is symmetric matrix? What is skew symmetric matrix? Yes, most of the questions which they
Yes.
ask, that is generally from the inverse of the matrix or the homogeneous equations and all those things. Okay.
Okay, sir.
Okay. Now let's talk about point number 4. The matrix B dash AB is symmetric or skew symmetric matrix according as A is symmetric or skew symmetric matrix. So this is also a property. Suppose you have given B dash AB and it's asking like, is this will be symmetric or is this will be a skew symmetric matrix? So this is a property that it will depend on A. If A is symmetric, so this whole combination will also be symmetric. This whole combination will be skew symmetric if A is skew symmetric. Okay. Next property is all positive integral powers of a symmetric matrix are symmetric. Means if you have any symmetric matrix, suppose A is a symmetric matrix. So if we'll do A square or A cube or A to the power 4, it will always give you a symmetric matrix only. Okay, but for skew symmetric matrix, if you will do odd powers, then you will be getting skew symmetric matrix. And if you will do even powers, then you will be getting symmetric matrix. You can remember it like this, that if you will do the square of, suppose you are doing the square of skew symmetric matrix, so what will happen? The negative will be converted into the positive thing, right? Negative square is positive. Let's remember like this. Negative square will always be positive, and if there is not any negative thing in the matrix, how it will be a skew symmetric matrix? Yes, in skew symmetric matrix, you will always observe that the upper part and the lower part is always same, and there will always be the difference of negative sign only. Okay, so if you do the odd powers of a skew symmetric matrix, we'll be getting skew symmetric matrix only. But if you will do the even powers of a skew symmetric matrix, you'll be getting a symmetric matrix. Any doubts in this?
No.
Okay. Now, if there's the problem, let's say, let's move unitary matrix. Okay, so what is a unitary matrix? It's saying a square matrix is said to be unitary if A bar dash into A is equals to I. What is A bar? What is A bar?
Is it negative of the matrix?
No, not negative. This bar shows conjugate. Are you aware of conjugate things? Complex number?
So A plus BI conjugate will be A
Yes,
minus BI,
yes,
right?
A plus B iota. So in complex number, we know what is the standard format of the any complex number, A plus B iota, right? So conjugate of this A plus B iota is always what? A minus B iota, right? So suppose if
Yes.
this is a complex number A, so this is A bar. Okay.
Okay, but in matrices, how if it does not have any complex elements, how do we get the conjugate?
No, like this is the condition. This is the condition. Then only like whichever matrix follows this particular rule, then only it will be called a unitary matrix. Otherwise, it will be not. Okay. Suppose you have a complete real number 3. What is the conjugate of this? It will be nothing but 3 itself, right? Yes. Suppose you
Yes,
have
yes.
5 iota. So this 5 iota is nothing but 0 plus 5 iota, right? Conjugate of 0 plus 5 iota is what? 0 minus 5 iota. Yes. So
Yeah.
we can find out the conjugate of any real number or any purely imaginary number or the mix of both. Doesn't matter. But it should fulfill this condition. If this fulfills this condition, then only you will call it unitary matrix. So the condition is whatever matrix you have, first find out conjugate of it. Then after getting the conjugate of it, is transpose it. And if you are getting A bar dash, multiply with A. And after multiplying, if it is giving you identity matrix, then only we will call it unitary matrix. Clear? Clear? Let's take an example. Suppose this example is given 3, 5, 2, 3 minus 4 iota. Let's write it here as well. Let's say this is 3, 3 minus 4 iota, 5 plus 2 iota, 3 plus 4 iota. And the questions on the unitary matrix has been asked actually. That's why I'm giving you an example here. 5 minus 2 iota, minus 2 minus iota, and this 2. Okay. Now let's assume this is your matrix A. Okay. To prove that it will be a unitary matrix, so first you have to identify A bar. Okay. What will be A bar of it? So the conjugate of 3 will be nothing but 3, right? Conjugate of 3 minus 4 iota is nothing but 3 plus 4 iota. Conjugate of 5 plus 2 iota is 5 minus 2 iota. Conjugate of 3 plus 4 iota is what? 3 minus 4 iota. Conjugate of 5 will be 5. Conjugate of minus 2 plus iota will be what? Minus 2 minus iota, right? Conjugate of this will be 5 plus 2 iota. This will be minus 2 plus iota, and this will be 2 itself. So this is your A bar. Any doubts in this? No, I guess, right?
No.
Okay. So now after getting A bar, you have to find out the dash of it. Dash means what? Transpose of it. So what will be the transpose of it? 3, 3 plus 4 iota, 5 minus 2 iota, 3 minus 4 iota, 5 minus 2 minus iota. This will be 5 plus 2 iota. This is minus 2 plus iota, and this is 2. So now you have find out A bar dash. Now your next work is you have to multiply A bar dash with A. So you have these two matrices, this one and this one. You have to multiply it, and after multiplying it, you must be getting identity matrix, and identity matrix is nothing but 1 1 1 0 0 0 0 0 0 3 cross 3. Any doubts? Any doubts in this?
No. No.
Okay. So sometimes a matrix will be given to you and they will ask, is this a unitary matrix? So you have to do all this procedure and then you will be able to find out. Okay. Now let's discuss the next matrix, that is Hermitian and skew Hermitian matrix. And in this, the condition is this will be a Hermitian matrix if Aij is equals to Aji bar. Means what? What does it mean? What does it mean?
Basically, like transpose but conjugate.
So what we
If I
have to
understand
do,
correctly.
how do we check? First, we have to do what?
We have to find its conjugate, then transpose it, and then check
Yes.
whether it's equal to it.
Yes. If it is same, so we'll call it, this is a Hermitian matrix. Simple, right? Now, let's talk about the property of it. So if A is Hermitian matrix, then AII is equals to AII bar. Means what? AII means what? The row number and the column number is same. It means it's talking about the diagonal elements. So for any diagonal element, the conjugate of it will always be same to the original element. It means it should be always a real number. Yes. So for any Hermitian matrix, it's necessary that diagonal elements should always be real numbers. Okay. Now, second point, a Hermitian matrix over the set of real numbers is actually a real symmetric matrix, and a square matrix is said to be a skew Hermitian matrix. So for any skew Hermitian matrix, what should happen? There is only the difference of the negative sign. Means this time you have to find out the conjugate, then you have to do the transpose, and then you have to multiply with the negative sign. And then if you are getting the original matrix, then you will call it skew Hermitian matrix. Right? Any doubts? For any skew Hermitian matrix, the diagonal element should always be what? Imaginary or 0. Yes. Why? Because this time we have to fulfill the negative thing also. That's why we need imaginary number or 0 number. Okay. Here we do not need to have negative sign. That's why we were taking real number itself, so that the conjugate will not change. Any doubts? No, I believe. Okay. Let's go further. There's the problem.
Sir, can we have an example of the skew Hermitian matrix? That I think it would be better, right?
Sorry, example of it.
Can we have an example of it, like just a rough example? I got
Yes, we
confused a
have
bit in
this
the
example,
skew
right?
Hermitian.
Do you want us to solve this particular problem?
Just the steps. Like first, it will be conjugate. Then it should be transposed, right? We just
Yes,
transpose
yes,
it.
yes.
Then that negative sign, how do we check it? Like,
Okay, okay. Suppose you have this original matrix. This is your original matrix A. This is your original matrix. So first, we have to find out its conjugate. So if I do the conjugate, what I'll get? So I'm doing the conjugate thing and the transpose thing together. I have no issue, right? I believe.
yeah, fine.
Yes. So the conjugate of 3 iota will be what? Minus 3 iota, right? Conjugate of minus 3 plus 2 iota will be what? Minus 3 minus 2 iota. And minus 1 minus iota conjugate will be what? Minus 1 plus iota. The conjugate of this thing will be 3 plus 2 iota. Conjugate of this will be plus 2 iota. Conjugate of this will be minus 2 plus 4 iota. No. Conjugate of 1 plus iota is 1 minus iota. Conjugate of this is 2 minus 4 iota, and conjugate of this is 0. Now, if we'll match this original matrix and A bar dash, you can see every element is multiplied with the negative sign. Yes, if I multiply this original matrix with negative sign, or if I multiply this matrix with negative sign, you will be getting the original matrix itself.
Okay. Yeah.
So A is nothing but A bar dash negative of it. Simple.
Yeah.
And in Hermitian matrix, what was happening? A is equals to?
So we conjugate and transport, then it is equal. So this, there is no negative.
Yes, A is equals to A bar dash. Right? Not dash, sorry. Yes, dash. A bar dash. Okay, so what is time? How much time it's left? 1 minute. Okay. Okay. Let's have the next thing. Okay. Let's talk about the singular matrix and this non-singular matrix. That is also a very important concept which we'll be using for solving any homogeneous equation. And it's very simple. Any square matrix, if we find out the determinant of that particular square matrix, and the determinant of that square matrix is 0, it will be called as singular matrix. Otherwise, it will be called as non-singular matrix. I believe everybody knows how to calculate the determinant of any matrices.
Oh, yes, sir.
In everyone, right?
Yeah.
Okay. So if we are finding out the determinant of any matrix, and if it is coming as 0, it will be a singular matrix. Otherwise, it will be a non-singular matrix. Now let's talk about orthogonal matrix. So any matrix will be called as orthogonal matrix if A into A dash is equals to A dash into A. So you have to check if the given matrix is the orthogonal matrix or not, and you will be able to do it by multiplying A with A transpose and A transpose with A, and these two should be equal and equal to the identity matrix. Okay, so sometimes the question is asked like this: a matrix is given to you and it will be asked, is it a unitary matrix, is it a orthogonal matrix, is it idempotent